Welcome at FAULHABER. We create motion. FAULHABER was founded in 1947 here in Schöneich, close to Stuttgart, Germany. And the core technology developed in the 1950s is the coreless winding, especially back in the 50s for DC motors of highest precision and highest efficiency. Out of this core technology, we meanwhile have a family of over 50 patents worldwide. FAULHABER is a family-owned company, meanwhile in the third generation. And what started here is now a group where we do have 13 international sites for R&D and production. And then there are a few more of them working for customers, for you, with the sales teams and the service locations. Within the group, we have more than 2,000 employees. Headquarters is still here in Schöneich, Germany, and the turnover was over these 270 million euros in the last year. My name is Andreas Wagener, and I've been responsible for the development of our third generation of motion controllers. I joined FAULHABER 15 years ago, and meanwhile, I'm responsible for the systems engineering here. Today, I'm going to talk about standalone operation of our motion controllers, the third generation, so using their scripting capabilities. And while I'm presenting here, Regina Kilp out of our sales team is my chat partner, and so you can directly place whatever questions in the chat, and she will decide whether this is a question to be answered immediately or whether we will answer and discuss this question after the presentation, because there is a question and answer session after the slides. We are talking about the motion controllers. When you followed our webinars during the last year, there's 3 families of drivers that we do have. First of all, the speed controllers here. So these are the ones here for direct speed control, either integrated devices or external drivers. And then there is the second generation of our motion controllers, some of them also with scripting capabilities, but here we're talking about the third generation with all these operating modes, and these are the devices here. Our third generation is a very flexible driver for controlling either position, speed, or current of our motors, and these drivers have been optimized for the FAULHABER motor portfolio, but they are not limited to the FAULHABER motors. What we can do is drive DC motors, brushless ones, or the direct linear motors. And to do so, we offer a very flexible selection of feedback connections. So, of course, the incremental encoders, either magnetic or optical, and then protocol-based ones for absolute information, so absolute single turn or absolute multi-turn. And then, of course, typical for motors in these sizes, either the linear Hall sensors or the digital Hall sensors, or combine these sensors with an incremental one. And then we can have analog information for speed and position, so like a tacho generator or a potentiometer. We build in multiple protection and diagnostic routines, and these are the typical devices here. So either the integrated ones with an IP protected housing or the open ones, so to be placed onto your carrier board, or the ones having the connectors, so standalone devices here. And for all of them, and independent from whatever communication interface they have, we offer the capability of using scripting, so operating them in a standalone mode. Standalone operation is when there is no operator around. So when the motor and the driver are operating with no PC and no PLC and maybe not even an operator. So they are alone and don't necessarily have any connection to the surrounding system. And there are basically 2 options. This could be a direct, let's say, analog control, where the controller is configured to auto start, and the target value for either position, speed, or torque is then calculated based on an analog or PWM input, or using the step pulse input, that's the step mode, or a quadrature input, that's the gearing mode. If you're interested in these operating modes, there are additional videos in our Drive Time channel to explain how to use these ones. Here we are going to talk about using scripting, so that's a little more complex. Again, the driver can be configured to auto-execute such a script and can even be auto-enabled. We use these local scripts then typically when we need to react to whatever inputs. So these are used for simple local automation. And for example, this could be to switch operating modes without being connected to a master, or to add a homing before we do one of these analog control modes. In order to do this, we interact with the discrete IOs that we do have. We have these digital inputs. Depending on the product, it's 3 to 8 digital inputs, which support either PLC or TTL thresholds. And directly within the drive function, they could be used as the upper or lower limit switches or as a reference switch for whatever homing sequence. And then there are alternate functions that can be used with these digital inputs to connect a second encoder, or to use the mentioned step direction interface, connect PWM input, which is then very similar to an analog input, or even to capture precision with the touch function. Or, and that's more interesting here, use them as free digital inputs within your scripts. The digital outputs, 2 or 3, depending on the device, are open collector drivers. So you typically would have to connect a pull-up resistor or whatever to define the high level of whatever signal that you're going to use in your application. Directly out of the drive function, they could be used to drive holding brake, or to signal a fault, or a status of the drive, which can be defined by a bit mask. Or once again, of course, use them as free digital outputs in your scripts. And then there are the analog inputs, 2 of them, which have a ± 10 volt native range and a dedicated ground pin. This one has to be connected to a reasonable signal, otherwise that's crap what you're reading out of the analog input. Typically, they would be used as free analog references for either the voltage, the torque, the speed, or the position. But you can also connect a feedback for speed and position, or use them as free analog inputs, for example, to read whatever analog sensor and even transfer the value to your master if a master is connected. To give an overview over the scripting capabilities, I will first present the used basic language and its motion control specific enhancements. And then I'll show a pattern of how to start scripting here, give an overview over the libraries that we do offer, and over the typical parameters that we have to interact with in these scripts. And then, of course, using the Motion Manager as your development environment. And there are 2 examples that I prepared, and a short summary with an outlook of what could be an extension. So the basic elements here of the language is, well, of course, we use variables, and variables could either be the global ones. So these are these 26 A to Z global variables. They are available all the time. And these ones can even be mapped to PDOs, so to communication objects used in CANopen or EtherCAT environment. Otherwise, you can allocate variables using the dim keyword, where you will allocate dynamically a variable which is either, again, a global one if the dim statement is used outside of a function, or it can be a local variable which is only visible within a function if you use this dim statement within a function. And so these are examples of how to use this. So obviously create a variable and assign an additional value, or read a parameter and assign it to a variable, or here for calculation. And then, of course, we do have the typical conditions, if, else, if, to react to different situations, for example, to the inputs. And these can be nested, of course. And then there are the loops. So there is a do loop, do while, or do until, or an endless one, and there is a for next loop which is available. So typical basic keywords and capabilities of such a basic environment. And then for arithmetics, well, of course, we can calculate. All the variables are integer variables, so only integer arithmetic is available here. And this, however, includes bitwise shifting if we need it. The logic is the typical ones, and again, extensions here to use bitwise logic to mask a single bit or react to a single bit that's changed in one of the status, for example. And the interaction with the drive function is all based on the objects that the drive is offering. So all the parameters are available in the object dictionary of such a drive. And reading one is using the get object statement within the basic environment, and writing to one is using the set object statement here. And then there are additional features, because typically you need to interact with time. Timing can be used either with countdown timer, where you have to define one of these global variables to be the variable used by the timer, preset the time, and then when the timer reached its end, so counting one is every millisecond, then you react to the timer being ended. Or you simply want to measure the time, again, define one of the variables. Here I'm using the variable t, but it could be any variable out of this age set. Start the timing, and then at your convenience, read the variable to detect how much time has passed. And additionally, we can have an event handler where we react to the status of the drive. There is a dedicated parameter collecting up to 32 different status bits, and we can hook an event handler to any of these bits, or even a mask of these bits here. And then we do support functions and symbolic names. So functions are used if you want to reuse activities or you want to create a better readability, and we'll see this later in the examples. And using functions, we can avoid using global variables for information which should be accessible only in a local content. So that's typical in all the programming languages, and that's supported here too. Within a function, you can use this dim statement to create a local variable, or you can use and access the global variables. And these functions can be collected into libraries, library files, and these ones would then be included using the include statement. So the include statement here in this basic environment is used for library files which are more like a header, or for code which is to be executed. The restriction here is the file to be included has to reside in the same directory where you store your script file. And then there is the define statement, which can be used like in a C environment or C++ to assign a symbolic name to a number or a symbolic name to a variable. So this is using text instead of a number, which of course makes your scripts much more readable. And then of course the dim here, I already mentioned that one, where you can allocate a new variable, either a global one or a local one, and this variable is then referenced by its name only. But these dynamically allocated variables can't be mapped to the PDOs, and they can't be used for the special functions like the timer or the event handler. About the scripting structure, well, it's free. You can do what you want. The interpreter is executing line by line, but our suggestion is to use a structure which is very similar to what, for example, the Arduinos would use. So in the beginning, have a section where you initialize your driver to whatever it has to do, and then have a main loop executing the same, let's say, step sequence all the time. And that could look like the one here on the right side. So read the inputs, and then depending on whatever step you're in, execute a dedicated action. And these actions could then, for example, be calls to a function, like in a code here. So up here, assigning variables, and then here is the endless loop where first the digital inputs are read into the variable that I allocated up here, and then there's a step counter variable, and depending on the step counter, we step either into action 1, up 2, or 3. So that's a suggestion only. You can do it in a different way, but especially if you want to be, let's say, in fast reaction, real time, like we will see this in my second example, then it's a good idea to not have any blocking calls in here, but to do this cyclically, like in PLC environments, for example. Let's have a look at our libraries. 2 of them are delivered with the Motion Manager. First of all, it's the motion parameters file, and that file is already included by default in our template scripting file if you open a new one. And this one covers all the most common parameters with defined statements. So it's like a typical header in a scripting and coding environment where you have all these defined statements which assign a name to a parameter number, so you don't have to deal with all these numbers if you're not that familiar with these ones. Definitely, it's much more readable if you use these ones that are predefined in our motion parameters. .pi is basic include file. That's what we defined here. The second one is the motion functions.pi. It's also distributed with the motion manager. It's in the examples directory of the installation. And here we collected a couple of functions which should ease your job, because these are basic functions that you typically need to enable, disable, or stop the drive, and even to start movements and wait for being there. Waiting for being there, however, is a blocking action. So consider whether you really want to use that one or use a different implementation here. As I mentioned, if you want to include such a file in your script file, at least that one here has to be copied into this directory where you store your script file. That's not necessary for the first one, because this one is more or less built-in capability of the Motion Manager scripting environment. And then there's a third one. Well, we called it MyControllLib because it's adding a few commonly used functions that are well, easing the job when you try to interact with the IOs mostly. Well, there are some functions for motion control too. So start a homing method that's not blocking, or start the predefined homing, and then check whether a homing is finished. So these two are non-blocking and can be called in such an endless loop to check whether either of the two actions is already done, and only then you would react and switch to a next step in your step sequence, for example. And then I think 2 very important ones which ease the job here is assessing a digital input or set a digital output here. And if we want to use them, they are included on top of such a basic file. And so the motion parameters.pi is always included by default. And then I added here the motion functions.pi and had to store the file in the same directory, of course. And I added the mycontrollib.pi. The mycontrollib.pi is not distributed with the Motion Manager. We will upload it to our support website. Otherwise, if you can't find it there, contact our MC support team at mcsupport@faulhaber.com. And then here is the remaining script, and we'll have a closer look in the examples. About the parameters that we typically have to use, well, obviously down here, target values. We want to access the target position, target velocity, or the target torque. And then we might need to react to the actual ones, position, velocity, and torque. And then if we want to interact with the state machine, it would be a control and status word. and most likely also the modes of operation to switch between different operating modes and modes of operation display if we want to check in which operating mode we are. And then there might be the profile parameters that we are using here. All of these parameters are covered with our motion parameters.py. And well, such a drive does have a lot of parameters, but usually these are the ones that we need to use. So it's only a few of them. About the development support. So that's the view of the Motion Manager. All the IDE support is done in the editor component here in the Motion Manager. And you can see there are different tabs for different scripts. And there's the syntax highlighting. And so that's the editor window. Place it where you want to have it. And down here is a status line, which tells you which of the script is loaded and which status you are here. Up here is the program control. And on the right side, you'll find templates, which you can drag and drop into your code. And down here, you can access whatever variable. These are either the global ones, A to Z, or the ones that are globally allocated using the dim statement. And if you are within a function where you do have a local variable, then you can also access, read or write such a local variable using the entry here. And up here in the headline of the Motion Manager, there's also an access to the scripting, because you can start the active one or stop the execution of a script here too. The actions that we do have on top of the editor is to actually download and run a program, or to single step such a program. And if you're either, mainly it's when you run them, you can pause them, of course. You can place a breakpoint here by clicking sides to the line, or you can stop execution. And you can download and save such a file without executing it. So the actions are write or load a program. And whenever you download a program to the Motion Controller, you will be asked in which of the 8 places of memory this one should be stored. So 8 of them, and you get this question whenever you hit the run button or a step button and the script hasn't been downloaded already. And then you can start your program either here in the control on top of the editor or on top of the Motion Manager door. Or you can have your script started automatically if you enable this in the drive functions window. And you can use the auto-enable power stage feature, also available in the drive functions environment here. And then, of course, testing it here and using breakpoints or pausing the execution as you like it. And then there are some extensions here. The Motion Manager offers some syntax check feature because it's an interpreter, and you want to make sure that you get an alert if you have any typing errors before it's actually executed. So you will find this typical red underlined line here because there's an extra column here. So this line here isn't executable. And while these errors are still detected, you won't be able to download the script because it can't be executed successfully. If you got any runtime errors, like for example a division by 0, then your script execution is stopped. And then within the FAULHABER error word, that's the parameter 2320, then there is an error created in there. And by using the standard error reaction capabilities of the Motion Controller, you can then select how to react to such a dynamic error. You can simply send an emergency, for example. The script is terminated anyway. If you want to make sure that your drive is not in, let's say, dangerous state, you might decide to switch it off or switch to a fault state of the drive. and you can of course set a fault pin to have, for example, an error LED lit. And then depending on what type of error it is, there are different error codes which will be displayed by the Motion Manager if the Motion Manager is connected. And then let's move to the examples. The first one that's distributed with the Motion Manager, simply to show the capabilities here is, well, first step, enable the drive and then move to a first position, wait a little time, move to a second position, again, wait a little time, and then start over. In that case, there are no requirements relating to the motion profile and no additional checks of any IOs necessary. So a very, very simple example, simply to get you started. So no additional wiring necessary at all. And now when we want to do this, then the idea is, well, start drawing. Try to come up with a step sequence of what you want to have and draw the different steps here and write the actions that you need within the boxes here and the conditions for switching from box to box besides the transition lines here. And then, of course, create or use functions, for example, to implement whatever action you noted in the box here. So let's check this. This is the first example, and let's switch to the Motion Manager and examine how this is working. To demonstrate the usage of the Motion Manager and scripting environment, I'm using one of my demo units here. This one is having an MC V3.0 SET, so the big one having the EtherCAT connections here. And on the front, there are these 3 switches to stimulate the 3 digital inputs. The 2 red LEDs are connected to the digital outputs. The green LED is for the power supply. And then there are these 2 potentiometers connected to the analog inputs. The motor here is 2232 BX4 motor, and there's a small disc to watch the movement. In the view of the Motion Manager, the motor is already selected and configured and tuning is done. And so what we now have to do is switch to the editor component of the Motion Manager, and the different scripts can be selected using the tabs on top here. I'm starting with the first example, which is an example which is more or less based on the standard example that comes with the Motion Manager. It's stored in the examples directory. And what we see here is a header which should carry a reasonable comment about what we are doing here. Next one is the section where the libraries are included using this include statement here. And then 2 target positions are defined in order not to deal with whatever magic numbers in the code, but to directly use reasonable names here. The real code is starting here with first switching to the operating mode, profile position mode, so position control, then enabling the power stage, and then there's an endless loop where we use a library command to move to a first position as an absolute move, wait until we are there, a small delay, this is 1 second, 1000 milliseconds to a second position, and then to have it a little more complex, disabling and enabling the driver once again before we start over. To do this, I will start with the single step mode. So first the program is downloaded to the driver, and question is which of the 8 spaces should be used. In that case, I'm using the first one, so program number 1, and then the execution is started here with the first line really executing code, which is setting the operating mode, and then by using the button here or the F9, I can single step, and so the operating mode is set, and then the drive is enabled, and I can hear a small noise coming from the motor now that the power stage is enabled. And here the endless loop is starting with the library command moving to first position, and then check whether the position has been reached. A small delay, these 1000 milliseconds, moving to the second one, and once again check whether the position is reached, and then disable, delay, and re-enable and start over. And this can, of course, also be done without single stepping, but more or less in real time. And so we can see the motor moving between two positions, and that's all for the first example. Okay, here is a second example that's a little more complex. In that case, I want to interact with the IOs, and the idea here is to create a script where initially when the drive is started, so after power up, we are executing a homing sequence to reset the position, and then after the homing sequence is finished successfully, we switch to analog control, and depending on a digital input, here it's a digital input 1, we either switch to analog velocity control or analog position control. Such a script, of course, could be auto-enabled too, and then this would be a fully autonomous operation of this motion controller here. Additional requirements here, the homing shall use the lower limit switch to generate the 0 position, and we are going to use the first analog input as the target for the position and have to scale that one accordingly, and the second analog input to create a target speed, and again we have to scale these ones accordingly, and the enable or disable of the drive shall be based on the second digital inputs. The configuration here is not part of the script. This is usually something that you would create beforehand and store in the configuration of the driver, so no need to do this by accessing a lot of parameters out of your scripting environment. If you want to know more details about these ones, check with our drive time channel, because there are the videos explaining how to use these analog inputs here. And then about how to implement this, well, once again, start drawing. So come up with the different steps that we want to have here at the transitions and at the conditions for the transitions, and write the actions into the blocks here. And after we have such a drawing, you can as well directly start coding this graph and filling in the missing parts here. So once again, let's switch to the Motion Manager and check this script. The second example is the more complex one, so that's switching the operating modes. What we can see here is, once again, there is of course the header, and then the section where the libraries are included, and some symbolics here. Of course, the drive is already pre-configured, so I pre-configured the analog inputs to be reasonably scaled for the purpose here, for analog position and analog velocity control, and I had to pre-configure the limit switch that is used here for this homing method. Homing method 1 is using the lower limit switch for homing, and this requires, of course, one of these inputs to be configured as the switch here. And here the switches are defined, so I'm going to use the first one here to switch between the operating modes, velocity or speed or position control. The second one is used to enable, disable the drive, whereas the third one is used as the lower limit switch. The sequence then is pretty simple. First, wait until the drive is enabled or shall be enabled by reading the switch here. Enable the drive, start the homing method, and then in an endless loop wait until the homing is finished, because homing will only be finished when the edge of this lower limit switch is detected. And then after we got our reference frame here, we start with an endless loop, where within the loop it's always first checking the enable switch whether the drive is still to be operated. If so, keep it enabled, and then decide whether we use position control or velocity control and switch to the operating mode that is selected. If this enable switch is no longer enabled, then disable the drive, and that's it for the example here. Using a lot of the library functions, but should then be relatively simple to be understood here. So to start this, I once again have to download the script to the driver, and in that case it's relatively complex, so I don't use single stepping, but directly use the real-time one. Storage place 1 was for the simple example, so let's use the storage place 2 here, and then we are in here and we don't see where we are. Well, there is a line counter down here that tells us in which line we are operating here. First one would be to enable the drive, and then the homing sequence is started. Sequence 1 is moving the drive to the lower limit switch. That's why it's turning counterclockwise here until the limit switch is reached, and that's what I'm going to simulate with the digital input 3 here. Okay, and now we are directly operating, and looks like we are in speed mode because here the drive is turning, and when we check the code here, speed mode would be the one which is selected when the input isn't active, and here the upper position is the passive one. So now I can change the speed here using the potentiometer, or switch to the position mode where the drive is directly following the potentiometer position here. And in the end, of course, switch it off again. That's it for this second example, and now let's switch back to a few summarizing slides. So here are the two scripts. That's what we had first. Comparing it with the example delivered with the Motion Manager, I only added the disable and enable here to make it a little more complex, but you can see here is an access to one of the parameters here, the modes of operation. So using the set object feature, and then the right one is a more realistic one where we really interact with the digital inputs here and change the behavior of the drive, and that's done using the MotionController library here and the isInput function, which is implemented in this MotionController here. And using this isInput, I can directly, well, I could use a number here, but we use the define statement to have the code more readable. And then the second one, again, the set object command here to change the operating mode, and so that's motion control specific extension of this basic scripting environment. That's about the examples, and then the outlook. The additional options that would be available is, of course, you could combine having a master and the local scripting. In such a case, the master would typically interact with the control word, the status word, maybe the target position or whatever, and would interact with the motor control capabilities, whereas an additional part of the logic in the master could call subroutines that you implemented in the scripting environment, and which of the subroutines is going to be started could be controlled by an incoming variable. Here I used the variable I, and then the status of this local subroutine could be reflected in an outgoing variable, for example, the O here. In that case, you could create a handshake between the scripting here and your master. For example, to reduce the number of parameters that you need to change, if you need to change, for example, the format of a machine or whatever, this can be used here. Or if you simply want to use starting a specific homing here, which is not one of the standard homings that would be available, and only after this one is executed, you take over with the master to control the behavior, for example, in profile position mode. But that's, I think, a little more complex. There's an application note about the capabilities here. You'll find it on our homepage too. But if you've got any questions, don't hesitate to ask. And then there's an additional one. You can protect your IP because you can set a passcode for others to be not able to read out the scripts when you distribute the motion controller to your customers. So the summary here is standalone operation can of course be based on the pre-configured analog control modes, But if you want to interact with the, let's say, digital inputs and outputs, it's using the local scripting based on this basic interpreter environment. And this scripting can be used and combined with all the products out of this third generation of motion controllers out of our family FAULHABER product environment. And we can even combine scripting with interacting with masters. We used the basic language here, and we added some motion controller specific enhancements. And typically that's using set object and get object to read and write the parameters of a drive. The FAULHABER Motion Manager, or PC software, is used for coding and testing. And the job of coding and testing is, of course, eased a lot by using these libraries that we created, or you can download from our support site. If you want to access the support site, here would be the link. And I think now it's the time for your questions. And on video. So, okay. Have there been any questions in this session so far?
Yes, we got some of them. Starting with the first one, can the program variables be saved?
Well, I mentioned a few of them, different program variables. They are the ones that you would allocate using the dim keyword, and these ones are transient, can't be saved. And then there are these predefined global ones, A to Z, so 26 ones. And these ones can be saved. That's been one of the requirements we received out of the previous generation of drivers, to be able to save them and reload them after a program has been restarted. And so, yes, these ones, these 26 variables A to Z, can be saved in our persistence memory.
Okay. And next question, how fast do the script run?
So speed of the script, well, we had these two examples here. The first one was using the delays, and so of course the execution time is dominated by the delays that we put into the script by purpose. The second one didn't have any delays in there, and because I used the same one for one of our drive time videos and wanted to know about the performance, I checked the execution time here, and that can be done by using one of the variables and toggling it, and then reviewing the cycle time in our graphic analysis tool. And so it came around with 4 milliseconds for the complete execution of the script. That's not like having compiled code, but it isn't bad. Anything else?
Yes. Question regarding the available space, or how big can such a script be?
Yeah, in total we got these 8 spaces to store code, but the distribution is dynamically. So you can even use the complete space for a single one, or distribute it between several of them. I think, I don't know it by heart, but we had a few times increased the space, and it should be close to 15 kilobyte now. 15 kilobyte nowadays, where every picture has several megabytes, sounds pretty compact, but printing the 15 kilobyte on paper can be confusingly long.
Okay. Next question, how do I protect my script against modification or copying by others?
Okay, yeah, that's been one of the last informations on the summary slide here. That's again a requirement that came out of our previous platform, where we also had scripting but no protection. In case you want to protect your IP here, there is not really a password because it's a numeric parameter, so it's a passcode. it's an unsigned 32-bit passcode that you can come up and assign to the scripts, and then these can only be read out after entering the correct code there. So I think 32 bits is complex enough for you to figure out a code that should be difficult enough to crack. And a second one is even the variables can be protected against following them. So there's a second code that can be assigned to the variables. So you could even come up with a non-understandable communication between your master when it's exchanging data with the script, the local script. So again, this could be kind of tarnished. Anything else?
Yeah, one more question. Can I have my drivers pre-programmed?
So you want to have the script file already when delivered from FAULHABER. Yeah, likely. I completely understand if you develop your script and then delivering maybe hundreds of them might be annoying to do this manually, driver by driver. Can be done. Our end-of-line station can pre-program your driver with whatever customized parameter set, and part of this can also be a script, a special script that you of course would have to share with us, and then we can pre-program the driver and deliver it to you directly pre-configured. Do we have anything else?
No.
Here?
No.
Doesn't matter. If you got any additional questions, don't hesitate to contact our MC support team, which would be mcsupport@faulhaber.com, or of course contact the local sales team. And aside of that, I think there's a next webinar here. So yeah, we do have one, FAULHABER drive systems for medical applications. That would be that's Tuesday, so it should be 2 weeks. Yeah, so you might have already received the invitation here. Otherwise, check with our homepage and sign in for that one here, medical applications. Interesting one, I think. Okay, so thanks for watching, and well, recheck with our channel here. Bye.